Hello students, we are going to cover nuclear chemistry in two sessions. In this first session, we are going to cover some basic facts related to the nucleus, some basic terminology which we are going to use off and on in nuclear chemistry, the stability of nucleus, various factors affecting that stability, nuclear radiations, their types, their properties, and some instrumentation. Let's start with the nucleus itself. As we discussed in atomic structure as well, the nucleus was discovered by Rutherford. It consists of neutrons and protons which are together known as nucleons. The number of protons, which is also equal to the number of electrons in the atom, is the atomic number of the element, which is denoted by capital Z. The total number of neutrons and protons, that is the nucleons, is the mass number of the element denoted by capital A. The radius of the nucleus is of the order of 10 raised to minus 15 meters. The volume is of the order of 10 raised to minus 8 centimeter cube, and the density is of the order of 10 raised to 14 gram per centimeter cube. We can visualize the atom of an element with atomic number 3 like this. This is the nucleus in which there are 3 protons and 3 neutrons, that is 6 nucleons, and these are the 3 electrons which are moving around the nucleus. Now let's discuss some of the definitions that we are going to use very frequently in nuclear chemistry. The first one is nuclide. A nucleus with a specific mass number and atomic number can be termed as a nuclide. Each and every element can be represented in the nuclide form. For example, if E is the symbol of the element, then we write E with Z as the subscript which denotes the atomic number of the element, and capital A as the superscript which denotes the mass number of that element. So let's take the example of uranium. The symbol of uranium is U. 92 is its atomic number which is written in subscript, and 238 is its mass number which is written in superscript. Similarly for lead, the symbol is P. Its atomic number is 82 and its mass number is 208. Isotopes. Those nuclides which have the same atomic number but differ in their mass numbers are known as isotopes. For example, these are the 2 isotopes of chlorine. Both have the same atomic number, that is 17, but their mass numbers are different, that is 35 and 36. So this isotope, that is Cl36, has 1 neutron more than that of Cl35. The next definition is isotones. Those nuclides which have the same number of neutrons are isotones. For example, C13 and N14. Both have 7 neutrons. Therefore, both of them are isotones. Nuclear isomers. Those nuclides which have the same atomic number and same mass numbers but differ in their nuclear properties are known as nuclear isomers. This difference in nuclear properties is due to the difference in the arrangements of the nucleons in the nucleus. For example, bromine 80 has 2 nuclear isomers which are denoted as bromine 80G and bromine 80M, where G stands for ground state and M stands for metastable state. Ground state is the lower energy nuclear isomer, whereas bromine metastable is the higher energy nuclear isomer. Let's take an example. Which of the following pairs is a pair of isotones? So 4 pairs of nuclides have been given to us, and we know that isotones are those nuclides which have the same number of neutrons. So first of all, let's calculate the number of neutrons in each pair. In the first pair, it is 35 minus 17, that is mass number minus atomic number. So the number of neutrons will be 18. And chlorine 36 will have 36 minus 17, that is 19 neutrons. The second pair, 12 minus 6, that is C12 has 6 neutrons and C13 has 7 neutrons. C13 again has 7 neutrons. Nitrogen 14 also has 7 neutrons. K40 has 21 neutrons and calcium 40 has 20 neutrons. So we can clearly see that this pair of nuclides has the same number of neutrons. Therefore, C13 and N14 are isotones. Nuclear binding energy. The energy which is required to break the nucleus into its constituent particles is known as nuclear binding energy. So if we know the binding energy of a nucleus and the total number of its nucleons, then we can calculate average binding energy. Binding energy per nucleon is known as the average binding energy. It can be denoted in the form of a simple formula in which average binding energy is equal to total binding energy divided by the mass number. Its average value is 8.5 megaelectron volt. It shows a specific pattern in its relation with the mass number of the elements. It first decreases with increase in mass number. Its value is maximum somewhat around mass number 60 and then it decreases. The average binding energy has maximum value for iron 56. This is the graph that we obtain on plotting the values of average binding energy on y-axis against the mass numbers on x-axis. As you can see, the value of average binding energy first increases. It is maximum for those elements which have their mass numbers somewhat around 60. Its value is highest for iron 56 and then its value gradually decreases along with the increase in mass numbers. Mass defect. Mass defect can be defined as the difference between the theoretical mass and the actual mass of the nuclide. This simple formula is used to calculate the mass defect of a nuclide. Delta M, which is the mass defect, is equal to Z into MP. That is the number of protons since it is equal to the atomic number. And MP is the mass of a proton plus A minus Z, that is the number of neutrons, into Mn, that is the mass of neutrons. So this particular part of the equation gives us the theoretical mass of the nuclide minus capital M, where capital M stands for the actual mass of the nuclide. The energy which is equal to the mass defect of a nuclide is responsible for holding together the nucleons in the nucleus. Now 1 AMU is equal to 931.5 MeV. With the help of this equation, we can calculate that energy.